It's always nice to see a lot of people face to face. 2 years ago, this place was almost empty, so it's always nice to see more and more people coming to this lecture today. Good afternoon, and welcome to the 2023 Paul Zia Distinguished Lecture. My name is Santiago Aguilar. I'm a civil structural engineer at WSP and current Zia Committee Chair. Today, we want to honor Dr. Zia's life, achievements, and contributions to our industry in today's lecture. We are very excited to feature the design and construction of the Allegiant Stadium in Las Vegas as this year's topic. For 22 years, the Paul Zia Distinguished Lecture Series has featured expert structural engineers, architects, and contractors from around the world, showcasing landmark civil engineering projects. I want to welcome everyone here at Stewart Theatre and also those joining online. This year, we're excited to share that we surpassed 1,000 registered attendees for this lecture, so we're super excited about that. I would also like to thank the faculty, civil engineering upperclassmen, graduate students, and the NCSU Civil Engineering Immersion Experience Program for joining us today. I also want to acknowledge the Zia family who are here today to remember Dr. Zia's life and legacy. Next, I would like to thank our planning committee for their hard work and perseverance to make this event successful. I want to thank Amy Alexander and Taylor Wamba from the department for all of their hard work to make this event happen today. At this time, I would like to extend a warm Wolfpack welcome to our speakers, Ellen Spangler and Frank Freudenberger, who have traveled from out of the state to present on the Allegiant Stadium project. Thank you for giving your time to support NC State and our local structural engineering community. We are looking forward to do this presentation. Finally, I want to thank the many sponsors who have made this event possible year after year. We are thankful to have so many sponsors come back each year to offer their support, and to have new individuals and companies sponsor this year as well. Our signature sponsor this year is Dr. Darren Holt. I would like to also thank our gold, silver, and bronze level sponsors. Your contributions go beyond today's lecture. The proceeds directly support scholarships and fund many enhancement programs for civil and structural engineering students at NC State, and perhaps most significantly, the inspiration that students receive from attending this event each year. For today's lecture, any questions at Stewart Theatre or in Zoom meetings will be responded after the presentation. We will moderate the questions and share them with the speakers accordingly. 2 PDHs are available for attending today's event, either here or virtually. We will send out the PDH certificates within 2 weeks. At this time, I would like to introduce Dr. Jim Fentner, Dean of the NC State College of Engineering. Please help me with a round of applause for Dr. Fentner.
Well, good afternoon, everybody. Thank you, Santiago, for the introduction. I'm so excited to be here today and offer my own welcome from the College of Engineering. First, let me thank the Planning Committee for this lecture, which always puts in such hard work. I'd also like to acknowledge all the staff who've worked hard behind the scenes. So much invisible work goes on in putting off an event like this. I'd also like to thank our generous sponsors. Each year, this lecture is incredibly well supported, and we couldn't do it without the community of individuals and companies that surround this department and always steps up to help make it happen. I'm now in my 2nd month here at NC State University, getting to know the campus. I'm proud to say I got here without the use of Siri or staff support. And the warm welcome I've received in the past 2 months is just incredible. This campus is friendly, welcoming, and excited for the next phase and the next iteration of the NC State College of Engineering. Among things that have really stood out to me that I've enjoyed so much is learning about the excellent traditions in this College of Engineering. And it goes without saying that this lecture series is one of those most important traditions. It serves as a tremendous legacy to Dr. Zia, and I know he and his legacy have meant so much to this department, college, and university, and personally to so many in this room. What I've learned about Dr. Zia is that he's an exemplar of what those of us in my profession should strive to be: an inquisitive researcher, a supportive educator, thorough and responsible administrator, and a humble and caring friend to so many. I know that he played a crucial role in making the Department of Civil, Construction, and Environmental Engineering as strong as it is today, and he was a pivotal figure in the academic field of pre-stressed concrete. I'm so proud that our College of Engineering honors his legacy with this lecture series. Next, it is my pleasure to introduce Dr. Rudy Saracino. Dr. Saracino is a professor of structural engineering and previously served a successful term as the Associate Department Head for undergraduate programs. He's here to represent the department today for Dr. Jackie McDonald Gibson, the head of the department, who's on international travel and could not join us. Dr. Saracino is a member of the American Society of Civil Engineers, the American Composites Manufacturing Association, the Precast Concrete Institute, and the Concrete Reinforced Steel Institute. And he's an elected fellow of the International Institute for FRP in Construction. He works broadly in advanced materials and systems that benefit critical civil infrastructure. Please help me welcome Dr. Rudy Saracino.
Thank you, Dean Fentner. I wasn't expecting that introduction. I appreciate it. Welcome, everyone. And on behalf of the Department of Civil, Construction, and Environmental Engineering, I'd like to also extend my warm welcome to all of you here today. This distinguished lecture series in honor of Dr. Paul Zia was initiated by distinguished Professor Sammy Riscala, who is with us here today, back in 2002. When I moved to NC State in 2006, and then attended what was the 5th annual lecture, it was located in the Monteith Research Center on Centennial Campus. A room that some of you might know that seated at most 70 people. This was, of course, in the days before Zoom, and so there was no convenient live streaming option. Today, as we heard from Santiago, we have more than 400 in-person delegates here today, with more than 800 joining us in Zoom. So it's incredible to see how much this lecture series has grown over the years. It is now the largest and arguably the most significant outreach event of the department. And the hybrid offering of this lecture series is realizing Dr. Zia's vision of reaching an international audience. In part, this is made possible by the generosity of our industry sponsors, and I thank them for their continued support of this lecture series and the department. I'd also like to acknowledge the commitment of the Zia Lecture Committee, all of whom are volunteers themselves and busy in their own practices. And in particular, I want to acknowledge those committee members who are representing our undergraduate students. And they are Jordan and Zoe, and our graduate student liaison, Ari, for all of their efforts and commitment to make today a success. And as was already mentioned by Santiago, we would be remiss if we didn't acknowledge the efforts of Taylor and Amy for making today happen. There's so much that goes on behind the scenes that would not be possible without their efforts. And finally, I extend my gratitude to our speakers today who have taken time out of their own busy schedules to be with us here at NC State and present what will surely be an interesting and informative talk on the design and construction of this iconic stadium. As was mentioned, we're honored to have here today several of Dr. Zia's family, his 2 children, Lee and May, and 2 of his 4 grandchildren, Sarah and Tessa. So thank you for being with us here and representing Dr. Zia. And at this time, I'd like to call May to the podium to say a few words.
Thank you so much. Of course, everybody knows that we lost our dad August the 16th. I will say that he kind of had a punch list as he was, thinking that this was going to be it. And one of them was to dictate a set of opening remarks for this lecture so that I might read them to you. And I'm going to read it just the way he dictated it. He said, "Ladies and gentlemen, after attending this lecture in person for 22 years, I regret very much that due to my health condition, I am not able to be with you today. For the past 22 years, this lecture was able to attract over 600 of our faculty and students and many local contractors and engineers. With the introduction of live streaming, I am pleased that this lecture has now been able to attract over 800 in attendance, many from outside of this immediate area. He would be thrilled at the number of people who are now attending today. The subject today represents a very important design and construction project in the West. As we know, this project is the largest sports arena in the Western United States. It is built in an area with a large population. As we often hear from our federal government agencies, such as NSF, EPA, and others, that to build a major facility in such as this arena, there will always be some environmental and social equity trade-offs. I hope our speakers today will be able to address some of these trade-offs in the design concept and construction techniques." There's your question. Thank you for your attendance today and your continued interest in this lecture series. I feel sure it will continue to showcase the intersection of engineering research and the built and natural environment. Thank you.
Thank you, May. We truly lost a humble and remarkable human being. Dr. Zia's commitment to graduate student education and research is recognized by the Paul and Dora Zia Graduate Student Award, which is made possible through the Zia Endowment. Eligible graduate students are nominated by faculty from the Structural Engineering and Mechanics Group, and the final selection made by the Departmental Graduate Programs Office. This year, I'm privileged to recognize two of our graduate students who are recipients of this award. Both of these PhD candidates are within a year of completing their degree requirements, and as you will see, they already have very impressive resumes. Their research is well aligned with Dr. Zia's legacy of translating innovative and transformative research to practice for the betterment of society. So first, our first awardee is Mohammed Kambar. Mohammed is co-advised by Dr. Giorgio Proestas, who's here, and Dr. Greg Lucier. His research centers around a large-scale experimental study of dapped end pre-stressed concrete double T beams. That's a mouthful, but we all use it whenever you're in a concrete parking deck or in buildings and warehouses and schools. His goal is to develop design procedures that account for lightweight concrete, various pre-stress levels, and high-strength internal steel reinforcement. His work is augmented by 3D nonlinear finite element analysis to study the effect of additional parameters. He interacts with industry directly to design and build his test specimens, which are large. They're in the order of 30,000 pounds, so he's dealing with large full-scale specimens. He interacts, which includes travel to the precast plants where he personally oversees and documents the fabrication process. Dr. Zia was actually an advisor to this research project, which was supported by the Pre-Stress Precast Concrete Institute, PCI, and he had the privilege of discussing his research with Dr. Zia on several occasions. Mohammed is the recipient of the Daniel P. Jenny Fellowship and the Alan Mattock Graduate Fellowship, both nationally competitive awards through PCI. He has published a journal already and has several others under preparation. He's a mentor to undergraduate research assistants at the Constructed Facilities Laboratory, and beyond his own research project, Mohammed has contributed to numerous other projects at the CFL and is a valuable resource to his peers. So with that, Mohammed, I'll ask you to come up and receive your award. Congratulations. The next awardee this year is Gina Alieva. She is advised by Dr. Abhinav Gupta, and her research is on simulating the complex problem of material degradation due to alkali-silica reaction, known as ASR, in concrete structures using finite element analysis. In particular, her research is related to the assessment of structural integrity for the long-term operation of nuclear power plants affected by ASR. Her model and the uncertainty quantification of the model has been presented at international conferences and is of interest to experts at Oak Ridge National Lab and the U.S. Nuclear Regulatory Commission. She's also working on several journal papers and has received sponsorship from the U.S. Women in Nuclear Program to attend their regional and national conferences. Gina was a participant in NC State's preparing for the professoriate program, and she has contributed to the teaching mission of the department. She's active in service too, most notably in the Civil Engineering Graduate Student Association, where she initiated several technical, professional development, and social activities for graduate students. As part of the Graduate Student Association, she has served as its treasurer and vice president and is a mentor to incoming graduate students. Gina, would please come and accept your award.
And now the moment that we've been waiting for. At this time, I would like to introduce our speakers, Ellen Spangler and Frank Freudenberger, who were a part of a great team of designers and builders for the construction of the Allegiant Stadium in Las Vegas, the fastest designed and constructed U.S. football stadium of its size. Please join me with a round of applause to welcome both speakers. I'm just going to go ahead and read a quick biography of both of our speakers. Ellen Spangler is a senior project manager at Mortenson Construction. Ellen earned a degree in architectural engineering with a focus on construction management from the University of Colorado at Boulder. After graduation, she was hired as a field engineer at Mortenson Construction. Ellen, who has worked at Mortenson for 9 years, is a senior project manager currently leading construction of the St. Louis SC Major League Soccer Stadium. Ellen has worked on 3 major sport projects leading up to the St. Louis MLS, including US Bank Stadium in Minneapolis, Minnesota, where she worked with the team handling heating, cooling, and life safety systems. Also, the Milwaukee, Wisconsin's Fisher Forum, where she was a key player in the structural steel phase and the scoreboard installation, and the Allegiant Stadium home to the Las Vegas Raiders, where she was the enclosure team leader. On the Allegiant Stadium project, she led the team to a successful execution of a difficult glazing metal panel and roofing scope. Ellen also led the formidable closeout effort working through punch list completion and substantial completion requirements, helping the team achieve an early an under-budget turnover of a landmark project in the midst of a global pandemic. With each successive project, she continually tackled the challenges head on the aims to apply each gained experience to the next project. Ellen loves construction due to its complexity and especially enjoys working on sports projects because they're high-profile projects that generate community excitement. Her ability to pivot and take on any new challenge thrown her way has been a huge asset to each project team she's part of. Again, let's do a round of applause for Ellen. Now, Frank. Frank Freudenberger is a structural engineer and associate principal at the Arup Los Angeles office. Before moving to Los Angeles in 2011, Frank worked for Arup in other offices across the 3 continents. In his more than 19-year career with Arup, he has delivered challenging and complex structures such as transportation facilities, high-rise structures, museums, and stadiums all over the world as structural engineer and or Arup's multidisciplinary project manager. As Arup's project manager and structural engineer for the Allegiant Stadium project, Frank and the Arup team delivered the structural and the facades engineering in an extremely short time frame. Again, we can just give a round of applause for both the speakers. And with that, you guys go ahead.
All right, first off, wanted to thank everybody for coming out today. Special thanks to NC State for having us, the Zia family, and the committee for putting on this presentation. Frank and I are very excited to share an in-depth look at Allegiant Stadium with you all, and so we'll dive right in. Wanted to go over our agenda really quick, so we'll do introductions, though I don't think we'll have much to say about ourselves to expand on that. Then we'll walk through the project story and overview of the structure. We'll talk about early decisions. We'll dive pretty deep into the structural design, and then we'll talk about our BIM strategy, our construction and delivery, and then we will leave a bit of time for questions, so if everybody can think of those while we're presenting, we'd be more than happy to answer anything at the end. So I'm Ellen Spangler. I work for Mortenson Construction, headquartered in Minneapolis. I think the rest of my bio gave you guys a pretty good insight into who I am, so I'll pass to Frank.
Yep. Hi, everybody. Likewise, I think we spoke. We already mentioned everything what I do. I'm based in Los Angeles and also co-lead the structural team there.
So just a brief introduction to Mortenson. So a family-owned firm started 69 years ago, started as a concrete contractor in Minneapolis and has grown substantially, do about $5 billion worth of revenue annually now. We've got 13 regional offices and then a handful of traveling groups. And so our sports division is one of those traveling groups. So I work for our sports and entertainment division. We've done about 30 years in the sports industry and have worked on over 200 projects scattered throughout the country, valued over $15 billion. We are consistently ranked in the top few sports builders by ENR. We do say, though, it's never our goal to be the biggest, but it is our goal to be the best.
Great, thanks. So I hope everybody knows Arup, but we are a global engineering enterprise. What sets us apart is like we are of independent ownership. We cannot be bought, and we are specifically set up that way so we are able to keep our independence. We have at the moment roughly 18,000 people in 95 offices in 34 countries around the world. Oops. My apologies. And then here in the Americas, we've been in the Americas for 37 years and have roughly 2,000 staff here. I know we're going to talk about stadiums today, but I wanted to show one of which I think like one of our best projects. Most people probably know the Sydney Opera, right? Then we were involved in the Marina Bay Sands. We did the Bird's Nest. We did the water cube next to it as well. And then we've done a series of these high roller. I think this is the one in Vegas. But we're doing everything. We're not just doing building structures. We're doing also like transportation structures, and that you see like one of the here in the middle. Is this one. This is the Fulton Street Transit Center in New York. And for those people who like the Batman movie, this is 2IFC, and what looks like a fairly normal tall building structure is actually one of the most efficient tall buildings in the world. So that's why I wanted to put it out there. So, aims, I think, it speaks for itself, but these are our guiding principles: quality of work, total architecture, meaning, you always need to consider all disciplines. And as such, we are providing all services. Humane organization, straight and honorable dealings, social usefulness, and reasonable prosperity. And with that, Ellen, you want to?
Yeah, so we'll jump into the project story and overview, starting with just a quick video to get everybody ready.
Okay, so you probably saw it already in the video, but this number is significant for the project, right? Because this number dictated everything. It dictated like how we design it, how we build it, how we permit it. And this number represents like the number of months it took from the design to the day when Ellen actually handed over the keys to the owner. So how did we do it? And a stadium isn't actually built in these 40 months, right? There is a long journey to it, and the journey of the Raiders in Las Vegas actually started 2012 with the Farmers Field Stadium proposal, which was supposed to be built in downtown Los Angeles, also with 72,000. And that was the first time we got involved with H&TB. And that deal actually fell through in 2015. So, and then the next steps actually started also when Mortenson got involved, Ellen.
Yeah, so there was another idea to move the Raiders to a shared facility with the Chargers, what is now SoFi Stadium, shared between the Rams and the Chargers. And the Raiders organization actually reached out to Mortenson. At the time, we were constructing US Bank Stadium in Minneapolis, Minnesota. And they said, hey, you're our builder of choice. We want you. At the time, we respectfully declined the opportunity because we just didn't have the capacity. We had a ton of team members engaged in Minneapolis to finish US Bank. We were right in the trenches of the ballpark down in Atlanta for the Braves. And then we were getting ready to start Chase Center, so the Golden State Warriors arena out in San Francisco. And so the timing just didn't work out. And so Raiders were pretty disappointed, but they understood and walked away. And that actually started a beautiful partnership between Mortenson and the Raiders. And so in 2017, the decision was made, the parcel of land became available, and the NFL owners all met and voted in, I believe, a 31-1 vote that the Raiders were allowed to move to Las Vegas. And a condition of that move was that the stadium had to be open for the 2020 season. So had to be ready for preseason games in August of 2020. Fortunately for the Raiders and for Mortenson, our capacity was looking a lot better, and so the partnership was able to continue out in Las Vegas. We started design with Arup in April of 2017. Design progressed, construction progressed, and then ultimately we finished the stadium one day early on July 30th of 2020. All right, so now we'll move on to how did we deliver the stadium? So obviously a stadium of that size, with that fast of a pace, takes a huge team. And so the organization that was the ownership group was a partnership between the state of Nevada and the Raiders. So that was the Las Vegas Stadco. And then Manica was the concept architect. So Manica came up with all the beautiful renderings that the Raiders organization fell in love with. Mortenson McCarthy, it was a joint venture, we were hired. And it was a design build delivery structure. So we had the architect and subconsultants under our contract, as well as all of our trade partners to construct the project. HNTB was the architect of record. You can see the other folks on the screen, most notably for today's discussion, Arup, the structural engineer. So we worked hand in hand with Arup, really from that April timeframe all the way through until the very end of construction. And then our trade partners are in the other blue box you can see. So we self-performed concrete on that project.
So a project of this size, can only be done with one team, and it needed to be, we needed to be clear on one goal to get to the success. What that means is everything had to be like subordinate to these goals, and to understand the background better, you need to understand football is the only revenue stream for the Raiders. So there was either a stadium on July 31st, 2020, or there was no stadium at all. So that meant simply, yes, you can come up with a scheme, you can come up with an architecture, you can come up with a design, a schedule, anything, but if it doesn't meet the schedule, if it can't be built, if it can't be permitted, if it can't be designed within these 40 months, then it's not the right scheme. You don't have a project. And you can see the design schedule is extremely compressed, with only 12 months from start to 100% CD, and then also we had to work closely with the permitting agency. Okay, so most of you guys are familiar with design design and construction procurement, and what you see at the top, which we call standard on this one, is standard, but it's typically not standard for a procurement of a stadium of this size. This is typically what's done in design bid build. So you design it, you finish your design, you bid it out, you permit it, and then you construct it. And as you can see, it's quite long. And if you start, like, let's say in March, actually in April 2017, you realize, hey, it's November 2021, ain't working, so you need to do something different, right? So you certainly need to go design build. So, but then you also need to accelerate things. You need to overlap things, meaning you need to have activities working in parallel. So meaning, for example, as you can see here, you needed to start construction, and that the construction actually starts before permitting is not a mistake, it's not an error. That didn't mean we didn't do anything. We didn't do anything wrong. It meant that all the civil preparation work had to start beforehand. There were like culverts which had to be replaced and other things. But you can see that 2/3 into the design we had to already procure permits. And then shortly after, for these permits, they had to start construction. And then other things is, permanent site presence, which is actually quite common for projects of this type of type and scale. Okay.
So we knew what the timeline was, and we had to sit down with the Raiders organization to figure out what are the architectural features that are must-haves. And so we developed a pretty short list, honestly, of must-haves, just thinking through, okay, we've got a stadium. The stadium's going to be built in the desert. Desert climate isn't all that friendly in the early or like the late summer for outdoor games, so it has to be enclosed. As soon as you have an enclosed stadium, you have to have air conditioning in order to keep people comfortable. And one of the Raiders' absolute non-negotiables was they had to play on a natural grass playing surface. And so we proposed a few times, hey, have you guys thought about turf? That would be a real schedule saver. That could really save this whole field tray that we'll show you later. And they were like, no, absolutely not. Must be natural grass. We don't care that we're moving to the middle of the desert. Got to be natural grass. So that was a design challenge, but we overcame it. And then the other big must-have were the lanai doors, as they were called during construction. So a series of 4 operable and 2 fixed doors that were 50 feet wide and 80 feet tall, that when the weather was nice, allowed you to open up to get just beautiful views of the strip. And so that was another must-have. So Frank and the team rolled up their sleeves and got to work.
Okay, so how did we make the stadium designable? So, the usual suspects, so starting off design repetition, pan choice floors, a limited number of connection types. Also such things as, maybe I should mention here, we as Arup, as a structural engineer of record on the West Coast, we designed all the connections from 200% CD. I guess it's different than what it's typically done here. So limiting the number of connection also helps, because it limits your design time. And then a large number of the connections were also capacity designed, and that is also a balance between the efficiency in the design versus making it efficient to build and making it efficient for changes. Because if something changes, you have extra capacity in your connection. You don't have to redesign. You can make on-site changes quicker. And then for people with seismic backgrounds, select a most balanced seismic force resisting system, SFRS, with an R equals 3. Some of you may think, oh, R equals 3. Why did you choose something relatively low, meaning you have fairly high design forces? The reason is because we were able to go around seismic requirements on the members and the connection design. And then parametric modeling and automation. We will go a little bit more in detail about like the BIM documentation, but cutting out time, important time, was absolutely essential to make the schedule. And then, structural separation. There were numerous iterations in collaboration with Mortenson McCarthy in the beginning. How are we going to separate it? Where the movement joint's going to be? And that also helped us to helped us with the design process, because as you can imagine, if you need to overlap design, you need to have like analyzing structures separately at the same time. Okay, so we had to cut it into pieces, and what this shows is like what we call, so what you see at the top is like the vessel structure. So you see like a vessel, right? That's why the name. On the outside, and that is a braced frame steel structure, fairly standard, and that sits on top a concrete plinth and outside of the salient structure. So it has like a movement joint. It sits on the concrete structure, but then it has a movement joint all around, right? And then you have 4 separate bowl structures with double structure movement joints. So what that means is like, you have a concrete plinth which is connected only at the foundation level, and then you have a movement joint through the steel and through the lower concrete structure. Okay, so what I already mentioned is we used a steel system not specifically detailed for seismic resistance. Doesn't mean anything bad, right? It just means you need to assume like a higher seismic force. Only is allowed to assume a certain level of ductility, as opposed to like, let's say, an R=8 system, right? So, and then because we had a vertical combination, these reinforced concrete cores were designed as ordinary reinforced concrete shear walls, also R=3. And due to that, because they were ordinary, also here we were able to reduce the detailing requirements to a, let's say, an acceptable, a constructible level. Okay, so I was already talking about like the importance of parallelizing the different work streams, and that also meant we had to work with the local authority, Clark County, to help them get it permitted in a time frame which would be acceptable to our client. Okay, so as we mentioned in the very beginning, you can't finish the design and then start constructing. You need to start constructing significantly earlier. So we needed 4. Not just 1, but 4 separate packages. And it's not that you just walk in and tell Clark County, hey, we're coming tomorrow and giving you like a set of plans. It was a long process. Probably one of the first meetings we spoke to them and got their feedback and input how we can do this the quickest way possible. And that actually helped us building a very good working relationship with them. Because as if the people who like paid close attention, you probably noticed that the ultimate owner is state of Nevada, which, some sense or not, is like sitting above Clark County, right? So they are like on one hand side, they're like the owner, on the other hand, there's like they're giving you a permit. So there were like these competing interests. We're saying like, hey, why does it take so long to review the structure? And on the other hand, it's like you need to do a good job, you need to be diligent, it needs to be absolutely safe. And the other thing was, we are like a large engineering company. We have our own software. We have our own way of doing things often. But that way of doing things often doesn't line up with how AHJs, like Clark County, do things. So we asked them, how would you like us to submit the documents? What software would you like to have it in? And of course, they used the software which we didn't have or didn't use in the beginning, which meant we had to change horses in like not halfway through, but early on. But that also helped them to verify and take a look at our models in software familiar to them, and that helped building the trust with them. And then regular on-site meetings during the construction was like another key point I wanted to add here. Okay.
Yes, so how did we divide the permits up? So we divided the permits up in the way that made sense for construction, but probably not in the way that Frank would have preferred from a design standpoint. So our first permit package was our foundations package. We got that package and got going right away. While we were doing foundations, Frank and the team were working on our lower and upper concrete bowl. And so at any given time, I think we were about 3 months ahead from design to construction. So not a ton of time for design change error, AHJs deciding they wanted something different. So we as a team made the decision to have the first 2 levels of the building be constructed in cast in place concrete, because that would give us time for our steel detailing and procurement. And so once we got to our main concourse level, which is the level most folks walk in on at Allegiant, we switched to an all steel structure, and the steel superstructure was the last the last permit package that we had. Okay, and how did we make it constructible? So we had to focus on engaging the trade partners that could perform with us as early as possible to make sure that we were hand in hand with our subject matter experts to make the best decisions for the project. So we really tried to make decisions backed by data, so either cost or schedule. We kept those customer absolutes I talked about earlier at the forefront of our mind, but there were a lot of decisions that had to get made very quickly. I would say the pro and challenge of design build is the contractor having the design team under our umbrella is it allows a ton more collaboration for those types of decisions, because the owner isn't as involved necessarily, as long as you're achieving the right design outcome for them. But it does offer opportunity for a little bit more disagreement or back and forth there in the beginning. We embraced common tools. So we'll have a whole section on this, but it was really critical to come up with a BIM execution strategy that everybody could live with and thrive in. And so we used Tekla for steel, and then converted to a like Revit, Navisworks, Revisto kind of combo at the follow-on trades. And we utilize continuous quantity tracking. We really tried hard where we could to get a repetitive design so that our folks in the field could get good at a few things and repeat and just drive up productivity and limit the surprises that we found. We did try to optimize and use bolted connections wherever possible to avoid welding fit-up issues. And then we tried very hard to either prefab or fabricate on site as much as possible. So we were able to fabricate off-site our transfer trusses, and they came in a few pieces, and then we were able, we'll see it a bit later in the presentation, but we were able to pre-assemble quite a bit of our roof steel so that we could make some pretty big engineered picks, but save a ton of time not having folks try to bolt up 250 feet in the air.
Yeah. Ellen, if I can just highlight, embrace common tools. So this, I think this is probably the most important decision which we as a team had to make, and which we made like early on, because common engineering practice, and I go a little bit into more detail later, is simply like outdated and takes too long. By using a shared Tekla model, we were able to cut out significant time out of the schedule. But also this one, no VE possible, right? If you look at a normal project, you do design, right? And you cost estimator goes off. There's like some cost estimator or the contractor which is on board does some cost estimating, comes back 2 weeks later and says like, oh, it's too much, right? And then you go back to the drawing board, change things. That wasn't possible, right? Because it was only like it's almost like a train, it's not that you can change lanes. You only had like one direction to go. So that's why we had like continuous quantity tracking, and that meant that we pulled out steel tonnages from our documentation models on a daily basis and plotted these on a graph. And it also gave us an inherent quality assurance process, because if there was like suddenly like a spike, then either there was like a big change, and if there wasn't a big change, there was an error somewhere, right? And by doing that, we were able to stay on track and avoid any VE. Okay. So the general structural arrangement. So the roof is built up of a cable truss and an ETFE roof, which sits just above the cable truss, which spans in between a cantilevered steel canopy, which cantilevers from the back and forms a compression ring. It's like kind of an eggshell thing. And compression ring, sometimes it's hard to imagine that why is this thing under compression? Just think about of a tennis racket. And you're trying to put some strings in between, and you pull, and you see like, oh, this thing is actually in compression. And then what we call the steel vessel on the outside, which formed like the skin structure, the brace frame structure, which is also steel bowl. And then we have like cast in place concrete bowl and concrete bowl and the retaining wall. Precast concrete bowl, and then the field tray and pile foundations. Okay, so now let's talk about the lower bowl and the concrete cores. Oops. So you can see, so this is like the 3D Revit concrete model, and what you see here in red and blue are these movement joints in between them. And you can see like each segment has like 2 concrete cores to provide the stability system for the bolt structure, the bolt steel structure. Okay, so foundations. So it's a piled foundations. The ground is actually quite good. However, there was like from an excavation perspective, it is difficult because most sites in Las Vegas feature a super hard caliche layer, and depending on where you are in Vegas, Las Vegas, you are not able to excavate these out with mechanical equipment anymore. So that's why excavation had to start early, and excavation was done with explosives. So they were like, was it on a daily basis, Ellen, when you blasted this out? So it had to be blasted out, and shortly after, once we received the permit for the foundations, we put in piles, and these were auger cast piles. Simply because of the scale, the number of piles we had, auger cast piles are just qualitatively the better pile, and through the large number you get a good repetition, and that's why it's like typically the most efficient pile system for such structure. One other thing was, and I don't know if we wanted to get greedy or if it was just like try to optimize it. We said like, okay, we do a test pile at each segment, and based on this capacity of the test pile, we may adjust like the number of piles and things, right? Which meant like we still had to like adjust the foundations and see. So as you can imagine, you're testing it, and your testing is not that far ahead, and you still need to go through like county approvals and other things, so as you can imagine, it was quite stressful, and it was like very difficult, when when the values didn't quite come up. So I think in hindsight it was maybe not the best idea. Should have maybe stayed like just started with the values of the first test pile. But one thing I wanted to show here, and this is like, you will see that through the entire presentation. There are like, outputs from our design, and it's not like analysis software. So these are custom written tools which help us to visualize design data and track and control DCRs and so forth. Because imagine piling was going on whilst we were already, whilst we're still designing the building, right? So we continuously had to check the pile forces, that we do not exceed what's already in the ground. And then on the right-hand side, just want to make the point, we used the, wherever we could, and we were allowed by code, we were using this lab on grade to tie these together for code. And common practice is to use the maximum column force at the maximum location and put the same reinforcing everywhere. But then you are like super conservative, We used scripts, and within 2 days, 1 day to calculate it out, another day to do QA and other things, we're able to optimize the reinforcing in the slab down. Okay, so this is like the lower bolt structure, the concrete floors, and in collaboration with Ellen's team, who performed a self-performed concrete. It was a cast-in-placed double T slabs, and this is just an example. But as you can see, we try to give the contractor as much flexibility as possible to allow them to adjust it wherever needed, so we can reach the maximum efficiency. Right? Okay, so I think when I see this one, I get like a cold sweats on my back. So as you can see on the left, this is like where the vessel comes down in the back, and as you can imagine, it leans, and there are quite high tension forces in there. So that's why in the GMP set, which was just basically issued just before permit submission for the foundations, we had these high strength rod pulling the tension all the way down into the foundation. So there was no steel cast into the concrete, and that's how we sized the concrete wall as well. Because so we had these bars, and then we had some confinement reinforcing around it, and it was fairly narrow columns for seismic conditions, right? And that was also done because we knew that we don't want to pull the steel procurement process forward, and because who has a W14 by 700 or whatever the size was laying around? Not a lot of people, right? So, but when the permit package, just after, maybe a month or so later, a new steel contractor came on board, and as the story goes, they had these columns laying around. And so in a moment of weakness, we said yeah, great idea, let's use the column and bring it into the concrete and cast it in, right? In hindsight, it wasn't a great decision because now we couldn't change the wall thickness anymore. And then we had struggled really hard to get the concrete in there, and we had to bring the rebar through the steel, and it took us a lot of 3D modeling of that connection to actually achieve what we wanted to achieve. So I guess the lesson learned here is, I think it through before you make a decision, right, on this one. Okay, so upper bolt structure. So, as mentioned, this is a steel structure, which has is supported laterally by these ordinary concrete shear walls, as you can see. So fairly standard. You can also see like some of these, actually 3 scoreboards, which was a problem in itself, because as usual, scoreboards are done last, but you needed to have like the supports in, you needed to have like a structure in, you needed to have some steel in, so you needed to have a support in, and then when Mortenson said go, we had to design it like very, very quickly. Okay, so this is the steel bolt structure. So there were 3 main concourse level, and then this one here, which you see in this, I guess, salmon color, is like a steel composite framing, and which created the diaphragm for the horizontal elements, which tied them back to the concrete cores. And those were like lightweight concrete, just to lower the foundation loads. But now this is like interesting and very important detail, as you can see. The raker beams are steel, but then the terraces were like precast. So if you want to save money and make it structurally most efficient, you would use these precast panels as a diaphragm. And it's often done, but the problem then is you need a temporary system to stabilize your steel during construction, which you then have to like remove later on. And typically your connection to the precast is more complicated and needs to be done afterwards. So by putting these in, you spend more money on the steel, on the permanent steel, but ultimately you speed up your process and ultimately save money, and that's why we chose it. Okay, so, and then you see like the grass retractable field on its way out, and we needed a 230 foot opening, 60 foot tall, and some people see these columns here. They had to go away, of course, because when the field run through, you can't have any columns. So what we've done was, so we wrote our basis of design, and then we spoke to the Clark County and said like, no problem. When the columns are not there aren't any people on it, so 0 life load, likely. And then the Clark County said like, how sure are you that there are no loads on it, no people on it? And then they made us to design for it. So the answer then was like, okay, we put these columns in, make them retractable, and and actually also wrote them an operations manual to make sure that, number one, when the columns are down, the field cannot be rolled out, of course. Number 2 is the stands have to be completely empty when you fold them up. And then number 3 is just in case people are, for whatever reason, you don't have the columns down and people are in there. We designed the trusses to span the 230 feet, but only for strength and only for reduced safety factors and reduced material safety factors, so that we are able to optimize that. And then, of course, for the deflection serviceability case, for vibrations, we were able to use these columns, and that significantly improved the performance and reduced the steel tonnage. And these were like hydraulically controlled, so that there is always they were always in compression when they're engaged. Okay, so here you just see like the scale, and these are like these are W40 inspired 700 pounds a foot pieces, right? This is heavy steel work, and 7 of them. And you can see like what scale it requires to transfer like a quarter of a stadium. No, and then this is a very, I think, a very impressive picture when you stand like on the pitch, and you just look up. And that was just, you see the compression ring at the top, and you see at that point, I think we just started attaching the first cables in the long direction, and you can see like how steep that looks like. It's quite impressive, actually. Yeah, and then I don't know if you can make out these little brackets. This is where the retractable columns attach to. Okay, and yeah, this is how the retractable columns look like halfway up, and oops, and then you can also see here there's a hydraulic jack, which once they're down, of course not when the field is there, but once they're down, that they like engage the truss into place. Okay, so the vessel structure, as you can see, like the braced frame structure, stability system. So now with the full canopy on top, and you can see like, oops, and then you can see like spans over the openings here and there. And then, of course, so erection. There was no time for like supported erection, because whilst Mortenson erected the roof, they were doing other things in the bowl. So everything had to be done like cantilevered. So besides like the permanent condition, we had to do. Entire design construction team had to do like an erection model to take into account like the additional forces induced and the additional checks required for the temporary conditions. And the concept was that alternating modules were erected, and then infill pieces were filled in. Okay, and then some images to that. You can see here one of these trusses being erected. Okay, so this is the compression ring, and I think I mentioned it in the beginning. This is like think of a tennis racket, and then it becomes quite apparent that this thing will be in compression, actually like very high compression. And only once this ring is like complete, you can only then you can start pulling the cables. Okay, so you have like these spaces of different height, which then by varying the height, you were able to create the geometry of the roof. And these are like, so you can see double cables, top and bottom, in each direction. Okay, so I really like this picture because on the left, because it shows you the scale. So this is Greg, one of the main designers of it. You can see like how big this thing is, right? And then this is the top chord of the compression ring. This is the bottom chord of the compression ring, right? And then here, this is also something which we were like very proud of. So these cables, they're not small cables. They're like, they were like 4 inches in diameter. They're big, and they're cut to length. They come to site. They're not, you can't just say like, hey, the compression ring doesn't fit quite. Can you make them a few inches longer, shorter? It doesn't work like that, And typically what's done is actually 3 options. Either you fabricate the compression ring to a much higher standard, and even if you did do that, you still are at the risk of having to adjust things on site. Second thing is you have like turnbuckles in there, which you can like adjust length, but often that's not wanted architecturally. And then we came up with this one because architects do not like, other things in the. And with this one, we were able to reduce the required tolerances of that compression ring and reduce the cost, but also give Mortenson McCarthy the flexibility to change things on site if things just didn't fit quite as much. Okay, operable doors.
Yeah, so the operable doors were actually installed by our curtain wall contractor. And so we had a very tight structural threshold with our crane. So pretty proud of these doors. We only had 5 inches clearance between the tip of the crane and the top of the door and structure. And so we're able to prefabricate these on the ground and then swing them into place. It all went fairly flawlessly. They're electrically controlled. And so for the first time in my career, the very first time we pressed the on button, the doors actually opened. So we were very excited here on a stadium that we had not very much time to troubleshoot errors.
Okay, so so I think I mentioned like there's the vessel structure, there's the internal structure, so they needed some slide bearing, and another thing we were really happy with, like this is how we thought it's going to look like, and this is how it actually ended up looking like. So we're quite, of course we didn't model all the connections in there, but you can see it's like similar, right? So. Okay, so normally when we give a presentation which is like has like significantly more focused on structural and automation, we go into significantly more detail. But what we've used on this project is like a database-driven approach, and what that means is we to make sure everybody works with the same data. We pull out geometry information, design data, and pull it into a database. So meaning, you have like a database for your overall geometry from your Tekla model. It's pulled into a database that can then be pulled into the analysis software, and you can run the analysis with that. At the same time, you can pull out the analysis results into that database, and then use any software. And software, pretty much everybody knows to visualize things. And this is just like here an example. For example, hey, show me the movement between these joints. And as you can see, this is like, these are actually 5 computer models pulled into one, which is difficult to do if you have like 5 different models sometimes at different stages. But this shows like the power of this one, right? Of this approach. Okay, digital design and BIM. So the next 20 minutes we're going to talk mainly about BIM. Digital design is a bit shortened just for the sake of time. But I think the BIM portion was probably the most critical thing on the project. Okay, so the eternal question is, or was, I think we answered it, is architects or steel fabricator software. So for people in the industry, they probably know, you're familiar with Autodesk Revit. It's very, it's the common program to document building structures these days, and it's a good tool for what it does. It's good for consultant coordination. It's good for concrete documentation, and it's great for interface with other disciplines. On the other hand, there's a tool which is better for steel. And 99% of all steel contractors and detailers use a software called Tekla Structure, which is owned by Trimble. So at the time when we started this project, these two didn't really talk to each other well. So the question really was like, okay, are we using the architect software for steel? Well, I guess, the architect told us, hey guys, you're using Revit, right? But there was still like, we still needed to cut out a significant amount of time out of the schedule, and just modeling steel in Revit is more difficult, This program was never written for complex steel structures, it just evolved. This one was written for it, and it was written for detailing and fabrication. And we believe that we are really good at that. So the other thing, what I think not good at the moment in the industry is that the procurement process is just lagging the technology. What's currently happening is like engineers and architects preparing all your structural and architectural geometry information in here. They have like a 3D model, but it's out of that 3D model they create like some setting out information. They plot the setting out information on a sheet, and then they say like, oh, here's your 3D model for convenience, but use the 2D information. And essentially the contractor fabricator rebuilds the geometry, and then you need to come back and check. Which is like kind of backwards. Why would you model it first, give it to someone else, have them build it, and then check it that they had it correctly built what you told them to build, instead of just like you build it yourself and then give it to them, right? So this is exactly what we've done. So now the question is just like, okay, what do you do for the coordination and documentation, right? So that's the question. So the question, the schedule is the answer. What I actually just told you. We in order to make this work, what I showed you in the beginning of the process, we needed these 3 months. So that was only possible with like cutting out a 3-month model creation on the detailing side, and that's how we did it. We built a level of development 300 model in Tekla at Arup. And then we had like a handover period where we sat with the steel contractor and discussed like, how do you want to have it built? Mill order, what do you want to have in the attributes, which data you want to exchange and other things, and then we handed it over to the contractor, to the fabricator. And that saved 3 months, right? But how did we deal with the coordination, architectural side of things, right? So because it's impossible to maintain these 2 models, because it's just like, oh, did you update it here? No, I forgot, right? Please, will you update? And it's like on such a compact schedule, it's just not possible. So nowadays, I mean, you have to go back like to 2017, now it's 2023. There are like some other tools out there. There were tools out there which like made them like talk to each other. But it was like fairly new at that time, and we had like delivered projects with our approach before, and we wanted to make sure that what we have works and we can troubleshoot it ourselves. So we used our tool, which we call Arup repository, aka repo, and it's like very simple, right? It takes you build something in Tekla, right? A simple. It's not simple, right? It's a stadium. And then you put that into, you read it out into a database. That's the repo, right? With like tools using API and Grasshopper scripts and other things. And that is your, what we like to call single source of truth, right? And that's the geometry. And then you use this one and build a native Revit model out of this data. And because it's based on the same database, it's the same. So the architect, I mean, they did know that we were doing this, but they didn't see it, right? Because they were seeing like a complete concrete and native Revit model. And by doing that, we could do both, give them both of the best worlds. We give the steel contractor the steel model and give the architect the coordination model. So,
All right, so Frank explained how the steel process went, and I'm going to attempt to summarize this graphic on the screen for how everyone else integrated into our BIM execution plan. So we made the decision early on that Revit was going to be the platform for the project for everyone else. That's fairly common now, I would say. In 2017, it was not as common. And so by getting our trade partners on board early as they were drawing their content straight into Revit, the design team was able to sync in the cloud and pull actually our trade partner drawn content into what ultimately would be the construction documents. So we were able to streamline that from what's typical, where the design team would draw the concept drawings and then the trade partner would go and recreate that in our construction modeling. So you can see the little Revit icon up there. And from Revit, every single day, we pushed to Navisworks. And so Navisworks is the platform for clash detection. And so that's where our trade partners were managing models and seeing the clash reports. That's fairly standard in the industry, has been that way for years. But we introduced a follow-on piece at the Allegiant project, which is the use of Revisto. So Revisto at the time was an emerging technology, pretty widespread now. And Revisto was how we pushed the model one step further and were able to assign issues and clashes to different folks. So it was able to have kind of it was easy to have a running to-do list for everyone. And it's a very easy, user-friendly program, I would say. And, you know, like, I could go in and create issues and assign them to Frank, and he loved that. And similarly, though, he could make issues and assign them to me. And so it was just a very collaborative process. And then each day, we would resync Navisworks and Revisto and kind of just chug away at those to-do lists, all the while, you know, transporting that info back to Revit to continue the design iterations there. And so ultimately, a very complicated graphic, but we were able to really streamline our approach by eliminating that time for design team created drawings and just going straight to trade partner creation for what was actually going to be built. And so this piece really just speaks to cutting out the waste. So we cut out the design team produced drawings from a non-structural standpoint by sharing all of our models up to the cloud. I want to say 2017 was really when the cloud was becoming widespread, and so now I think it's pretty common. Everybody probably uses it, but...
Yep. So, I mean, this is just another fairly complicated, you know, matrix graph of a very simple concept. You know, what it's trying to say, like, you know, this piece here, you know, typically fits somewhere in here, right? And now moved in onto like the design team side. You know, these things, you know, traditionally have been done like by the contractor, but it had to be done in sequence because they needed the information to do it, and then they did it, and then they rejected, and then they went on. Now you can see it's like more like a linear process, a parallel process, and by doing that, you save time. You also reduce interface, and reducing interface always means reducing risk of errors, mistakes.
So now we'll shift gears and speak specifically to the construction and a few challenges that we had. So necessity drives innovation. I would say that when we first sat down and scheduled this project out, it was not a 31-month time frame for construction. And so we had to come up with some pretty aggressive and bold strategies in order to achieve the construction milestones that were necessary to be able to open by July 31st of 2020. So our GMP was established in 2018, and right away mass excavation began. So our original plan was kind of a traditional excavation approach, and right away the soils report that we had received was off a little bit on how much caliche was in the soil, and we actually had significantly thicker bands running in a majority of the site, so we had to take a detour and go to the blasting approach. We then moved into our slab on grade construction and our concrete pan and joist construction to pave the way to start steel erection in, I believe, September of 2018. So we had just a hair under a year of steel construction. It was a 28,500 ton job. So multiple crews working in two different ways around the bowl in order to facilitate that. And then ultimately we got to our roof canopy, which prepared us for our cable net, what we like to call the big lift. Do you want to talk about the big lift?
Yeah, I mean, I just want to, on the big lift side, I just wanted to say, you can only lift this thing if the cables fit, right? And if the cables don't fit, you need to adjust, typically you need to adjust the truss, the truss, the canopy, and the compression ring. But with this schedule, there was no time to that, and that's why the adjustable node connections also helped to achieve that, and helped everybody stay on track.
Yeah. Our original schedule contemplated waiting until steel was all the way complete to start curtain wall, but once we had that original schedule, we had to find a way to start faster. So we worked with Arup. We kind of optimized the curtain wall connections in the ideal load case scenario, and we're able to start the lower level of curtain wall ahead of finishing structural steel. And then ultimately kind of moving into 2020 and on to completion, it was your interior finishes, seating bowl, all of that good stuff to really transform it into a stadium. Wanted to speak specifically a little bit about construction sequencing. So you can see on the left the actual, and then on the right is a tool that we like to use. We call it the 4D model. So it takes the construction schedule and integrates it in with our 3D modeling. So the very first challenge we had, you can see it on the screen, kind of a green snake running through the site. That was a box culvert. There was an existing box culvert on that parcel of land that was governed by the Army Corps of Engineers. And so in the site as the stadium was contemplated, it would have required us to move the box culvert. And so we sat down with the Corps of Engineers and we said, okay, we're gonna move your box culvert. And they said, why don't you just move the stadium? And so after a few meetings, everybody got on board with moving the box culvert over. So that was the very first thing we did, which really paved the way to be able to start construction. So blasted about 900,000 yards of dirt, and then started with two separate crews working clockwise and counterclockwise around the bowl for concrete. And then we followed that same path for steel. And then we'll go to the next slide and take just a deeper look at the structural sequencing. So the green items that you can see on the screen is kind of the current activity in progress. Purple that follows next is if there's another activity in that same area. So an example, green would be erection, and then purple would be steel detailing. And then it grays out when the activity is complete. And so we're able to use this to look at crane roads, swing radiuses, all of that to make sure that we're not trade stacking, make sure we're keeping people in a safe working spot. And I think you can start to get a feel for just how many activities we're working concurrently. So our construction schedule when we finished, construction had over 45,000 activities in it. And so a pretty monumental effort to get the structure completed. And so wanted to chat a little bit about the challenges. So we call this beating the house. So from 2017 to 2020 was a bit of a tumultuous time in the United States. So right off the bat, we started the global tariff wars. So we were really fortunate that the majority of our steel procurement was done ahead of those global tariff wars. But we did deal with the tariffs for a lot of our trickle-down commodities, and so we saw pretty big impacts to mitigate in our mechanical scope of work specifically, as well as a few smaller trades. Steel fabrication, our timeline was so quick that we had to utilize multiple fabricators across the United States. We'll dig into that in a minute. The cable net big lift, it was the first time Mortenson had ever performed such a feat, and it's not a terribly common selected choice in the US, and so there were just a lot of unknowns surrounding how the big lift was going to go, and it was absolutely critical for us because the way cable net structures come together is all of the cables were laid down in the bowl, kind of woven together like a tapestry, and you had your top strands and your bottom strands, and they wait there. And then as soon as the compression ring was done, it was time to start the big lift. And so you do a very cool sequence of lifting operations, and the entire roof is lifted slowly over the course of several weeks. And it was critical for us to be able to get that off the ground because we only had a 2-week period of time in our schedule to be able to set our lower bowl precast. As we entered 2020, we got hit with the COVID pandemic, and so a lot of uncertainty. I don't know if you all remember, but the Vegas Strip actually shut down for COVID. All the casinos closed down, which is the first time that's ever happened since Vegas in modern day became what it is. And you know, we rode kind of back and forth on, is the job site shutting down, is it not, all the way through, but ultimately remained open through the entirety of COVID until our finish line in July. And we were faced with bringing 2,000 people to work every day because naturally COVID hit right when we were at our peak workforce. So we had to bring 2,000 people to work every day. We had to get what is inherently an industry of teamwork and close collaboration, 6 feet separated. Our primary messaging for safety and for what's going on site happens in our morning meeting. That was all of a sudden scrapped because there wasn't a way to do it safely with 2,000 people. We didn't have an area big enough to keep people 6 feet separated. And so a lot of challenges, obviously. That was early pandemic days, and so we were seeing just changing recommendations, I mean, almost on an hourly basis. And so we're masking, we're not masking, we're social distancing, we're not social distancing. And so just keeping up with that. And ultimately, we're quite proud of our world-class safety record. So we were able to achieve a 0.98 TRIR on that project, which is about a quarter of industry standard. Vegas is not a community that's known for being particularly safe on projects. Unlike other areas where you would walk in and be the biggest job in town as a sports project and be the job that the community is the most excited about, it's just not that way in Vegas because we were a multi-billion-dollar job. At the same time, 3 other multi-billion-dollar jobs were being built. And so speed is usually what wins out there over safety. And so we worked very, very hard to change that narrative on our construction site, and we're pretty proud of our safety record. All right, I want to talk a little bit about our project network. So from a steel standpoint, we had 23 fabrication shops at the peak of our fabrication. And so that required a daily, sometimes multiple times a day check-in just to make sure that our steel was progressing the way it should. We had a few procurement challenges on that project, and so we were tracking, I mean, down to the individual pieces of steel coming from all over the country in order to get our erection done on time. We had a local staging yard, and we had sometimes upwards of 100 trailers of steel waiting to go on site. And then wanted to just briefly talk about our design assist team. So it really did span the globe. We had contractors from all over the United States working on this project. And then we had worldwide trade partners as well. So our cable net system, some of our steel came from Europe. And then the ETFE, which is that translucent material for the roof, is also out of Germany. And then ultimately, what did those results look like? Because at the end of the day, if you can't achieve the right results from a project, it really doesn't feel that great turning it over. And so we were able to achieve over the project goals in every single category, which is something we were really proud of. So there was some legislation with it being a partially public funded project that set some goals. There's a 15% goal of small business enterprises, and we were able to achieve 23%. The criteria for those businesses was a bit different than what we're typically used to seeing, but it had to be a small business that's primary licensing was in the state of Nevada. We awarded to many diverse firms, so 63% of the firms that we awarded work to were considered diverse firms, and it was 34 different firms that performed over $70 million of the work, and 70% of the work was from Nevada-based entities, which was very important to our customer. We were also able to award to women and minority-owned businesses. There weren't any specific goals created for this project, but it's a goal always of Mortenson's to make sure that we're spreading the work out so that we can help to build up the community. And so we were proud that we were able to award $86 million to those two categories. And then speaking specifically to the workforce participation, 63% of our workforce was either minority or female. And that's something we're starting to see an industry shift, and we're really, really trying to encourage specifically women to enter the workforce. And so we were excited to see that. We achieved 2% veterans, 14% apprentices, and then 80% of the workforce was Nevada residents. So at a time when COVID hit, Las Vegas got hit specifically very hard because the hospitality industry did shut down. And so to be able to keep those dollars flowing out into the community was absolutely critical at that time frame. And so just to wrap up, Frank and I are both very proud. Allegiant Stadium was delivered one day early and under budget, and it is the fastest modern day NFL stadium ever constructed. We did work about 7 million work hours, put 12,000 people through orientation, and again, we're able to achieve absolutely world-class safety performance on that job, ultimately wrapping up on July 30th and into just a landmark project for the area. And so with that, we'd like to open the floor if anybody's got any questions.
Who was the licensed engineer that sealed all the structural components? Was that you?
It wasn't me. It was the principal in charge, Attila Sekioglu, who was with Arup at that time.
Hey there, thanks for the great talk. With most of the procurement being done so early on in the project and with the design assist approach, how did you manage to keep costs under control and under budget?
Yeah, absolutely. So we engaged our trade partners in design assist contracts. And so I would say that that varies. Your typical contract with a trade partner would be, $10 million, and I'm going to provide 100 toilets and 4 showers, and the list goes on. And our contracts were written very differently. It was that they were going to provide the program required for an NFL stadium, and so we had phenomenal partners, and we worked tirelessly with them in order to optimize exactly what we were buying, making sure that it was the very best buy that we could get, and then if there were ideas that our trade partners have, I like to use the example, our mechanical contractor came on board and said, hey, we really don't love the way you guys have your pipe rack designed. It's not very efficient for us. It's going to cost a ton of money. Hey, we'd really like to do the chilled water loop this way. And that'll save for us and save for you. And we were able to optimize that and include it into the project because they were brought on board so early. So I would say say a combination of really smart like VE and getting our trade partners involved early, and then really making sure that everyone was bought in together on the design assist process.
I feel like I need to channel my father, who would always ask a question. I actually have two, and I'm not a structural engineer. But you mentioned that the field was retractable, so I'm just why is that? Is that for repurposing? And the second question, maybe a little more serious, is do you see the potential for generative AI to help with that language translation between the two different database things?
Yeah. Okay. So, with respect to the field, the radar's goal, one of the key principle was we need to play on a regular grass. Like they didn't want to have any artificial surface. But at the same time, we needed to hit like certain solar values for the roof, but that did not allow enough light into the structure to allow the grass to grow. So, of course, you can bring in lamps in and other things, but they also wanted to use like for other tenants to use the lower surface for other things. So that's why it was made retractable and it could roll out. And whilst in the outside parking position, you can have like venues on the inside on a concrete surface. So that's number one. And then I think the other question was like use of generative AI on the translation. In general, AI and other things, have their or will have their part in structural engineering. Absolutely. However, on this one, it's I don't want to say it's simple, but it's like a translation process, right? It just means like, okay, here's an API. Take this data, write it into a different format, into a database format, and then from the database format, generate it in a different format, And for that, you do not need the generative AI per se, right? But for in the future, for other purposes, AI absolutely.
You mentioned your safety program was successful, and you talked about orientations, but your project's over 30 months long. So what did you do to keep that fresh throughout the project, and maybe hit some numbers? How many people did you have on the site at one time, and how many safety professionals did you have helping them out?
Yeah, so we brought 12,000 people through orientation. At our peak, we had 2,200 workers on site every day. And so we had, at our peak, 5 safety professionals dedicated to the general construction side, and then we had our own safety for when we were self-performing concrete that was considered separate. So we did a number of things to keep the messaging fresh, because it can get stale pretty easily. Quarterly safety lunches out in Vegas were absolutely huge. I cannot say enough nice things about Mark Davis in that capacity. So I have never had an owner of a sports team show up early to a safety lunch, serve lunch, participate in the raffle, and then stay as long as it took to get every single item autographed or handshook or whatever that our craft workforce wanted. And so the Raiders organization bought wholesale into that. And so every quarter was a chance to just refresh that, like, hey guys, you're doing a great job, let's keep it up mentality. And Mark was hugely integral to that. We also started our Finish Safe, Finish Strong program out in Vegas, and so that brings in kind of a committed at the top mentality. So we would bring in at various critical stages of the project the executives and ownership level of the firms and ask for just a renewed commitment to safety. And then we also, completely converse to that, brought everyone who was 4-person level in for kind of some roundtable talks, and we sat down and listened and said, what do you guys need to be successful? Like, what can we do to help you have a better work experience? And so, you know, some things are really easy. They wanted popsicles when it was hot outside. And so, like, sure, all day long I can go walk around and hand out popsicles when it's hot outside. And it was just small things like that. For a lot of our craft workforce, it was the first time that anybody had ever asked them, like, what do you need to be successful? And so we saw huge dividends from that. And then also just not sacrificing the quantity of overtime to get the job done, because there's a lot of studies on burnout from overtime and how you start to see kind of diminishing returns on that. And so we did work overtime on that project. We worked a lot of overtime. We had shift work. We had all of it. But we were pretty religious about making sure that every few weeks folks got a full weekend off to go rest and recharge. And I think that was pretty critical too, because previously on jobs in Vegas, there were folks who had horror stories of, I've worked 16-hour days for 400 days in a row without a day off, and it's just not sustainable.
Yeah, would you mind going into going into a little more detail about the expansion joints that you have? I wasn't quite clear. Is the whole roof and the compression ring its own independent structure?
Okay, so so the vessel structure is one independent structure, and then you have like inside you have like 4 segments of like the bolt structure with the with the steel and concrete bowl. So there were like so if you count, so there is like one movement joint between the basically one ring movement joint between the vessel structure and the 4 internal structures, and then along the 4 internal structures you had like 4 movement joints as well. Does that make sense?
Yeah, I just wanted confirmation of the whole ring and the roof.
No. The ring and the vessel is one piece, right? So it's like this, and then inside there's a movement joint to the inside structures, and that's why we needed these like these bearings where to support the ends of the internal bolt structure. Great.
So I'm going to try to paraphrase the question I believe my father was getting at here, where he said there's when you build a major facility like this, that there'll always be some environmental and social equity trade-offs. And so the question might be around, what adjustments or accommodations did you have to make for the neighborhood, for the traffic control, for the air quality that must have been, horrible when you were doing all of the excavation, right? Did you have to displace neighborhoods, and what kind of accommodations went along those lines?
Yeah, so I would say that this parcel of land was actually pretty fortunate in Vegas that it was a completely vacant plot of land before we arrived to it. And so we did some neighborhood site improvements. I mean, what was like some rundown parking lots and stuff like that, we resurfaced for some improvement. And our main focus, given that we weren't displacing people or businesses or families, was to make sure that we were focused on incorporating as many firms in the right capacity that we could to enhance the construction in the region. And so we were able to divide our scopes appropriately to award, give somebody just starting out with their firm, just give them a small piece, but maybe that's what they need to get a bigger piece next time. And so we were pretty fortunate that worked out. And we actually had our last pre-bid interest meeting for our finishes trades down the road, and one of our rebar suppliers got up and he actually shared with the group, he was like, this is a project you want to work for. He was like, they treat you well, they treat your workers well, they pay you on time, it's funded. And so what has historically been not the best place to perform construction, we were able to really positively impact the community. As far as environmental impact specifically, the Raiders have a sustainability goal, and so they're a very minimal waste facility. There's quite a few enhancements they've made since the time that we did construction. I think that they turned cigarette butts into energy and all sorts of creative things. But specifically, we were challenged with coming up with the correct parameters for opening those big doors, because it really makes no sense in Vegas to have it be 115 degrees. You've built an entire enclosed stadium that is not terribly, kind to the environment with the amount of cooling that it needs in order to have all the folks comfortable, and then you choose to open the doors. I mean, it just makes no sense. And so we came up with some very specific parameters to try to be as eco-conscious as possible for when those sorts of decisions would be made.
Yeah, maybe if I can just expand. So with respect to project location, so this is the I-15, and then this entire plot was vacant, and I think the next, there are like now parking lots here, but I think the next hotel was like quite a bit away, beyond another overpass down here. So of course, there's always like a slight impact, but it was minimized by the, let's say, I mean, it wasn't remote, but it was like outside of densely populated area. And then with respect to like sustainability goals, there's such thing just to like reduce the embodied carbon through optimization as much as you can, and the example on the roof, for example, is on the doors is, when you open the doors, technically you would have to design the roof then for like a significantly higher internal wind pressure, and would significantly increase, member sizes. It may not even work and other things, So we were like then working with Clark County, wind consultant and others to make sure that we can design the roof for a minimal internal wind pressure. But in order to do that, we had to like restrict the time when these doors could be open. Like, for example, on game day, it would have to be checked like a number of hours before the game, like the wind speeds and the forecast as to where the wind is going to develop. And based on that, a decision was made, like, okay, you can have it open or closed. And only because of that, we were allowed to keep the internal wind pressure low, and by doing so, like, keep the structure fairly efficient. And a similar thing for the entrances.
All right, we have a few questions on Zoom here. I think we got time to answer a couple of them. Samir wants to know, did you use any structural design software other than Tekla?
Yes, we did, and Tekla is not at least at that time, it wasn't a structural design software. I mean, okay, I'm standing back. So Tekla is mainly a steel documentation software. Yes, there is a Tekla steel designer now, but at that time it was like, let's say, not developed to a stage where we wanted to use it. So we started the project off with in our own software, Oasis GSA, to do initial studies. But then, for multiple reasons, we also used Strand 7, if people are familiar with that. But then once we've had conversations with Clark County, they wanted us to use CSI software, and that's what we ended up using for it, for the analysis, or I should say, like, for most of the processing. Post-processing was in most cases done by our own tools. which I shared at least to some extent here.
All right, and I'll try to ask these in the order that came here.
Yeah.
So next question is, what is the role of the building department in these kinds of complicated structures?
Yeah, so the building department is responsible for ensuring that the contractor follows the design documents as produced, and that the design documents follow the applicable codes for the area. And so, you know, Vegas has had sort of a storied past with the building department. And so what used to be probably a very easy jurisdiction to build in, and kind of a lot of things slipped through the cracks, they've undergone a tremendous transformation, and it's actually become, I would say, one of the top 2 communities to build in. The second difficult community is actually Atlanta. And so Frank told a story this morning.
Yeah, so, you know, there was, yes, I can go into detail there, but, you know, the building department is going to give you the building permit, right? And the CFO in the end, and that's, and for them to do that, they want to be sure that you follow the code, and that's what they do, you know. So previously in Las Vegas, there have been instances, or one instance where the, you know, the inspector didn't do its job correctly, or in fact, like, you know, helped, you know, or facilitated that the construction didn't follow the actual construction documents. And then when it was found out later, they found that the building wasn't compliant with the code. And then, you know, it had to be like deconstructed, demolished, and, you know, lawsuits and other things. So the Clark County Building Department was like, you know, I want to say under scrutiny, but they were like really diligent, and they absolutely wanted to do a good job, despite of being like also under pressure to work as quickly as possible with us, you know. And on this point, you know, a great compliment to Clark County, who was a great, who were like a great partner in finding the right balance between like being conservative and but also being like collaborative and helpful, you know. And Ellen, I think you can confirm that, you know, we've ended up having like a really good working relationship with them at the end. And I think without that attitude, we wouldn't have been able to achieve that, building this structure in that time.
Yeah, we were actually the only project that Clark County's ever awarded a full certificate of occupancy on the first try. So they're used to doing either partials or temporary certificate of occupancies, but we were able to be awarded our full CO the first time we tried. So that was I think just like the ultimate culmination of teamwork there at the end.
All right, Frank and Ellen, I appreciate your time. And can we give one more round of applause, please? So my name is Ben Melke. I'm chair-elect for the ZIA committee. On behalf of the committee, we'd just like to thank our sponsors again. We'd also like to thank everyone who attended both in person and virtually. Dr. Zia will be very proud. Unofficial numbers are in, and we broke a record this year, so thank you so much for attending. I do want to mention and cordially invite everyone to next year's lecture. We already have a topic. Can you click the button, Frank, for me? Yeah, so next year's topic is going to be the Frederick Douglass Memorial Bridge in Washington, D.C. So we don't have a date yet, but we have a topic, which is great. So we encourage everyone to attend next year's event. There is a reception following this where you can speak more talk with the speakers and have some refreshments. So we invite everyone to that reception. Thank you again.